Placing single atoms in graphene with a scanning transmission electron microscope. This paper was published in Applied Physics Letters in 2017. In it, we describe how single atoms can be introduced into suspended single-layer graphene using a focused electron beam. We also show how a threefold coordinated silicon dopant can be moved step by step through the graphene lattice, illustrating the atomically precise movement of a single atom. The fabrication of material structures, atom by atom, has been a long-held dream of nanoscience. This capability would enable the creation of atomically precise structures that could be tailored from the atom up to exhibit desired emergent properties that have applications from quantum computing and quantum sensing to deepening our understanding of physical and chemical processes that occur at the atomic scale. To accomplish this, we need to learn the basics of how to manipulate atoms one at a time. Here we are using the focused electron beam in a scanning transmission electron microscope, or STEM, as our manipulation tool. To make the system as simple as possible, we use a single layer of graphene as our specimen, so that we can uniquely identify each atom instead of looking at a projection of a 3D specimen. If you Google graphene, you typically get perfect-looking rendered images of the hexagonal lattice, like this. But in the real world, graphene usually comes with a bunch of surface contamination that must be dealt with before you can get good images. Here's an example overview image of suspended single-layer graphene. Most of the contrast that you see is the contamination on the surface. The graphene itself is almost as dark as the vacuum. One benefit this gives us is that most other atoms appear much brighter than the graphene and so are very easy to see. If we zoom in, we can now begin to pick out the periodic graphene lattice as well as some brighter silicon atoms that have attached to the surface. The accelerating voltage used here was 100 kV, which is above the knock-on threshold for graphene. As a result, as we image the specimen, we gradually observe more and more beam damage because we are continually ejecting carbon atoms from the graphene. Occasionally, we also see these silicon atoms attached to the graphene. We hypothesized that the silicon atoms were attaching to vacancies or some other defect sites that were created by the beam damage, and that by scanning the beam across the specimen, we are sputtering a few silicon atoms off the nearby contamination and into the defect sites. The question is, can we do this intentionally? Start by moving the stationary beam to the desired location, dwell for a few seconds to generate some defects, and then move the beam onto the surface contamination to sputter silicon atoms onto the defect site. It turns out that this works fairly reliably if one chooses a location that is within a few nanometers of the surface contamination. Here's a before image. The red circle denotes the area that we will damage using the E-beam. Here's an image after damaging the lattice. And then we scanned the beam over this bit of surface contamination for a few seconds. A silicon atom was ejected from the surface contamination and is now attached to the defect site. Now that we have a method for placing silicon atoms in the graphene lattice, we can explore what other atomic scale transformations we are able to drive using the E-beam. After quite a bit of trial and error, we discovered that we could move silicon atoms step by step through the graphene lattice. First, we insert silicon atoms until we get one that is threefold coordinated, meaning that it sits at a single vacancy site surrounded by otherwise perfect graphene. Then, we lower the microscope accelerating voltage to 60 kV so that we are operating below the knock-on threshold for graphene. This is to prevent additional damage to the specimen. Then, we define a subscan box within which the beam can remain scanning, but that we can also reposition manually. When the beam scans over this subscan box, we generate a real-time updating image of the sample. In this way, we can see what is going on and react to the changes as they occur. Using this method, we found that we could lead the silicon atom through the graphene lattice and ultimately move it from a starting location to a target location, representing an atomically precise positioning of the atom. Links to the publication as well as the archive version can be found in the comment section below.